Hello everyone, today I'm going to talk about a paper which Viewpoint shows it best, language for weekly supervising view selection in multi-view instructional videos. Video understanding research has greatly matured over the past years and significantly helped tasks like activity understanding, robotics, video question answering, self-driving and many others. In this talk, I'll focus on instructional videos in particular. So, what are instructional videos? They're basically videos that are made in order to teach somebody how to effectively perform an activity. The web is full of such videos, from videos on how to pack a suitcase like Marie Kondo to videos on what to do after you attend the call of nature. But why are such videos so helpful? First, they offer a visual demo of how to perform a certain activity. This greatly accelerates learning. Second, the videos usually also come with an audio stream which not only captures the different sounds produced by the activity but also the speech of the demonstrator. This results in a very immersive experience for the learner. Third, the videos usually provide a detailed demonstration of all steps involved in the activity, no matter how important they are. This allows people with different levels of expertise learn how to do the activity. Fourth, they are usually posted on the internet, which makes them available to people from different communities at a low cost. This helps in democratizing learning. Finally, sometimes these videos are made by experts. In such cases, you basically get to learn the best practices from the pros. So, how does a typical instructional video look like? It looks something like this. As you may have noticed, the camera viewpoint of an instructional video switches depending on what stage the activity is at. Sometimes the camera view shows a close-up of the activity, and sometimes it shows a wide-angle view. But how do you make such a varying view video? The tradition has been to either do a post-capture editing of a multi-view video or perform active camera control when shooting the video. However, both these processes require manual effort and as a result are laborious and time-consuming. This naturally raises the question how to automatically select the most informative view sequence for making such a video. To answer this question, we tackle the task of view selection in multi-view instructional videos. In this task, given the video of an instructional activity captured using multiple cameras, the goal is to select the best camera view at each point in the video. So, what do we mean by the best view? In the context of instructional videos, the best view refers to the view that most clearly shows the salient aspects of an activity like important actions and objects and human body movements so that the activity can be replicated by someone trying to learn it. In this example, the first view is considered as the best view as it shows the person's hands, the wheels, and the action being performed more clearly compared to the other views. Note that compared to other scenarios in automatic cinematography, where the goal is to optimize for high level understanding and viewing pleasure, here the objective is to pick a view specifically for the low level understanding of the instructional activity. This increases the objectivity of the best view definition and makes our setup better posed and easier to evaluate. Solving this view selection task has important real world applications. First, as we saw earlier, it can be used in the post-capture editing stage to create informative how-to videos that a human can consume and use for skill learning. It can also potentially be used in energy-conscious capture settings where it's not feasible to keep all cameras on at all times and instead you need to smartly decide which cameras to use at which point in the capture. Existing work can be classified into three broad categories. In the first one, we have temporal video summarization, where the goal is to stitch together the most informative clips from the video and create a concise visual summary. In contrast, in view selection, you have to choose a suitable view from multiple given views and do that for each video clip. In the second category, we have active next view selection. In this body of work, you train an embodied agent to smartly control a camera for performing tasks like scene completion or object recognition. In contrast, in view selection, you are already given the different possible camera views and you are required to choose one view from them. Finally, the most related body of work is automatic cinematography, where the goal is to select a camera view sequence for showing an activity. However, existing methods are not designed for instructional settings. Moreover, they require large-scale labels for training. This makes video summarization and active next view selection adjacent but distinct tasks, and automatic cinematography the most relevant literature for our work. My research comes with two key challenges. How can we design view selectors specifically for use with instructional videos? And how can we reduce the heavy reliance on large-scale labels, which is common with existing methods in automatic cinematography? The key idea that we introduced to tackle both these challenges is that we use view-independent activity descriptions, which are also commonly called as narrations, to implicitly reason about the quality of different views. Before diving into the details of the idea, let's first see how these view-agnostic narrations are produced. For a controlled multi-view capture setting, a human annotator is asked to watch all views of the video and note down a detailed caption of the activity. For an in-the-wild capture, narrations are usually the demonstrator speech transcribed to text. So, how do we leverage these narrations to tackle our key challenges? First, we use these narrations to infer the most important actions and objects in the activity. Next, we use the salient concepts to infer which view shows them most clearly and subsequently choose the best view. More concretely, we introduce a model for performing view selection in label scale settings. Our model is called LangView. In this method, we use the view-agnostic activity descriptions, or in other words narrations, to provide weak supervision during our view selector training. Alright, now let's dive into the details of the first method. In this work, we tackle a view selection task where, given a multi-view instructional video, the goal is to choose the best view in the complete absence of best view labels. Here the key idea is to use text descriptions of the video to provide weak supervision to bootstrap the view selector training. Specifically, given a multi-view video, we feed each view to an off-the-shelf video captioning model, which produces a view-dependent caption for each view. Next, we compare each view-dependent caption with the view-agnostic ground-truth narration of the video to compute a quality score for each view. As I showed earlier, these ground-truth narrations are provided by human annotators who watch all views simultaneously and write down a free-form description of the video. Finally, we choose the view with the highest quality score from above as the best view pseudo-label for this particular instance and use it to train the view selector. Our method for this idea consists of a best view pseudo-labeler and a view selector. For the pseudo-labeler, we use k different off-the-shelf captioners. Each captioner takes all views as inputs and produces a view-dependent caption for each view. Next, for each captioner, we compare the predicted caption with the ground truth narration to obtain a quality score for each view and use these scores to rank the views. Finally, we aggregate the per captioner ranks using a rank aggregator module that extracts the consensus of all initial rank sets. Having multiple captioners vote on the view quality and then using a rank aggregator to consolidate the initial votes reduces captioning noise and improves pseudo-label quality. We take the highest ranked views according to the rank aggregator as the pseudo-label set for the video clip. Note that this set can have more than one pseudo-label depending on how many views are ranked the best. Our view selector consists of a view classifier and a relative camera pose predictor. The view classifier takes all views of the clip and embeds them into fine-grained visual features using a large encoder. It then maps the fine-grained features into more coarse-grained features and finally feeds the coarse-grained features into a classification head which produces an estimate of the best view pseudo-label. We set the training loss for this classifier to the minimum of the cross-entropy loss between the predicted view and each member of the pseudo-label set. This loss formulation encourages our classifier to predict as its estimate whichever pseudo-label it finds the easiest to predict. This stabilizes training and improves classification performance. Our post predictor takes the fine-grained visual features for each possible pair of views as inputs and predicts the relative camera pose between the views in the pair. We train the post predictor using an average cross-entropy loss between the predicted and the ground truth relative camera pose, where the average is computed across all view pairs. The rationale behind having the post predictor is the following. Since the captioners in our pseudo-labeler are trained to predict the same view agnostic narration, it can sometimes lead to a lot of views being pseudo-labeled as the best view, even though that is not the case. This could lead to the collapse of our view selector's features. The post predictor prevents this collapse by increasing the view dependence of our features and improves generalization to novel instances. We evaluate on two multi-view instructional video datasets. The first one is EgoExo4D. Each multi-view video in this dataset consists of one egocentric and four exocentric views. Moreover, the dataset has both physical scenarios like basketball or rock climbing and procedural scenarios like cooking or bike repair. Finally, its narrations are free-form text descriptions of the activity being demonstrated. Our second dataset is Lemma. Unlike EgoExo, Lemma videos have one ego view and only one exo view. Besides, Lemma consists of only household scenarios like watching TV or watering plants, and its narrations are in the form of verb and object annotations per a predefined vocabulary. These two datasets together let us test our model on a diverse set of scenarios and camera configurations. We perform both automatic and human evaluation of our model. For automatic evaluation, we take the caption generated using our model's predicted view and compare it with the ground truth narration using standard captioning metrics like CIDR and Meteor. We also compute the accuracy of verbs and objects in the predicted captions using metrics like verb IOU and noun IOU. For human evaluation, we ask multiple human raters to rate our predicted view against the predicted view of two top performing baselines and report win, loss, and tie percentages. Here are our results for automatic evaluation. We compare against a bunch of different baselines. The first set of baselines are naive heuristics like predict ego at all times or randomly pick a view. Our next set of baselines tries to pick a view that maximizes the visibility of interactions between the demonstrator's hands and different objects, or maximizes the visibility of their body. The next baseline is a state-of-the-art view selection model. The final baseline is an alternative but naive way for using language. For this baseline, we pick the view that produces the longest caption as the best view. This assumes that the longest caption carries the most amount of information about the activity. Our model outperforms all baselines on both datasets across all metrics, showing the benefits of our language-guided training. Here are our human evaluation results. In human evaluation, we conduct two studies. In the first one, we assess the quality of our best view pseudo-labels. Specifically, we ask human evaluators to rate the best and worst views per our pseudo-labeler. In the second study, we ask human raters to compare our predicted view against the predicted view from two top-performing baselines. On both studies, our model's predicted view performs the best. This highlights the high quality of our best view pseudo-labels and also our selectors' predicted views. Here we show our view selector at work on an EgoExo4D video. On the left you will see all views for the video. In the center you will see our model's chosen view. Note how our model chooses the ego view when showing important holds. On the other hand, it picks an exo view when the climber moves on the ground, looks away from the hands and feet, or falls down. Here is a similar example from the Lemma dataset. Note how our model chooses the ego view when the person is looking at their hands when interacting with objects. For example, when the person takes the cup from the shelf or pours the milk. On the other hand, it picks an exo view when the person is moving across the kitchen or when they are not looking at the objects involved in the activity. For example, when the person was closing the fridge but their head was turned away. We notice two common failure modes. In the first one, our model picks different views for the same activity across different instances. This probably happens because for these instances, the model picks on spurious visual cues that are not relevant to the activity. In the second mode, there are multiple good views that show the activity equally well, and our model chooses a view that always does not match the preference of a human evaluator. In this instance, more than one view can be considered to be the best view for showing the ball pass. For example, EXO 1 and 2, but our model picks EXO 2, which doesn't match what the human rater picked, which is EXO 1. Our model has some important limitations. First, our model doesn't explicitly enforce temporal smoothness in view transitions. These can sometimes lead to sudden view changes, which could lead to an unpleasant viewing experience, even though human editors are also known to make such hard cuts to maximize informativeness. The trade-off between view quality and viewing pleasure is an important aspect of view selection that needs to be rigorously studied in future work. Moreover, our model requires large-scale multi-view video and narration pairs for training. Even though multi-view videos and narration pairs are pretty general purpose, they can only be obtained in controlled multi-camera capture setups. Despite these limitations, Lang View is a promising first step in view selection in instructional videos.